Good morning, ladies. Welcome on board. I hope you're doing well. Thank you for joining me. And I have four speakers ready to roll and talk about a very special topic. This morning, the focus has been on materials. You've heard from two speakers talking about different type of materials that they're working with. And I have put together this panel to help us further understand some of the innovations that are happening within the materials space for additive manufacturing. We titled this panel Driving him forward through material innovation. And the speakers that I have with me this morning, the first person is Sarah Wolf. She's an assistant professor at Ohio State University. We also have Shruti Ratan. She's a staff research scientist in the materials team at Carbon 3D. Ramona Rafaz, Rayasfar. She's an assistant professor in the Department of Mechanical and Manufacturing Engineering in Ontario Tech University in Canada. And lastly, we have Nadia Kuretem. She's an assistant professor from Utah State University in the Department of Mechanical and Aerospace Engineering. Welcome, everybody. We're excited to have this discussion with you this morning. I believe some of you stayed around for the first presentation. You can see that we are really talking about material. We're looking forward to learn about the work you're doing within your labs, within also industrial space, how this material innovation is translating from lab to actual in the industry. I will start by giving you a mic. I'd like a bit of introduction from each of you so that the people can get to know you a little bit. I will start with Sarah, if you can start with a short introduction about yourself.
Hi, everyone. My name is Sarah Wolf. As Addie mentioned, I'm an assistant professor at The Ohio State University in Columbus, Ohio. And a little bit about me. So before that, I was a professor at Texas A&M University. And then before that, I was a fellow at Argonne National Lab. And then I have my PhD from Northwestern University in mechanical engineering. And what I work on is mostly on the metal space. So some of the materials that I've printed using laser powder bed fusion, but most notably directed energy deposition or lens, include titanium alloys, nickel super alloys, a lot of stainless steels. But recently I've been exploring high entropy alloys and using process monitoring, especially some synchrotron imaging, and I think Nadia will talk a little bit about synchrotron too. Synchrotron imaging or thermal imaging, or just even any kind of in situ sensors during the process to find ways to develop new types of metal alloys, but also metal matrix composites. And then I'm really interested in all types of materials branching out. So I've also looked at lunar regolith simulant materials, kind of like moon dust, as well as a bone simulant material like hydroxyapatite. So all types of materials, and this is a fascinating topic.
I want to say I love this panel. I feel like we put together the right people. The expertise here is just mind blowing. I did my PhD focusing on synchrotron X-ray imaging, and just knowing that could be something that people in additive can use, but it hasn't gotten a lot of momentum. And I'm looking forward to both of you sharing a bit about that so that we can direct people towards that direction. Nadia, you're up next.
Thanks, Addie. So as you mentioned, I am an assistant professor in the Mechanical and Aerospace Engineering department at Utah State University. My background actually starts with a little different, a little farther from additive manufacturing, where I specialized in high-speed imaging for fluid mechanics. So during my graduate school, I was looking at all of these awesome techniques for experimental characterization of fluids. And then moving on to my postdoc at the University of Utah is where I came to learn about additive manufacturing, and I dived more into that topic. So I have investigated and continue to investigate the process structure property relationships in metal additive manufacturing using advanced characterization methods. So on the process side, I'm interested in synchrotron imaging, as Sarah mentioned, as well as the powder properties. At the structure level, I use SEM in order to understand the underlying microstructures, and then CT scanning for porosity. And then on the property side, I'm interested in understanding the behavior of these additively manufactured materials using different approaches for testing.
Thank you. Ramona?
Okay, so hello everyone. Hello, Adi. Thank you for having me here. So my name is Ramona Fayasvar. I'm from Ontario Tech University, UIT, located in Canada, Oshawa, Ontario. I'm in Mechanical and Manufacturing Engineering Department. I'm a material scientist, got my PhD in Material Science and Engineering. So my expertise and research topic include multidisciplinary areas of additive manufacturing or 3D printing, with a focus on development of advanced composite and non-composite material, polymeric composite material, compatible with low-cost additive manufacturing or 3D printing. Also, I work on surface engineering, advanced coating, smart coating, and in terms of application for biosensors, point of care diagnostic, and health monitoring applications. So before joining Ontario Tech, I was a postdoc in University of Waterloo in multi-scale additive manufacturing research group, that one of the largest additive manufacturing facility centers in Canada. So I'm happy to be here.
Thank you. Shruti, you next.
Hi everyone, I'm Shruti Ratan. I'm very excited to be here. As Addie introduced, I am a staff research scientist at Carbon 3D. It's a very cool 3D printing company located here in the Bay Area in California. What I love about Carbon is that we have a confluence of material scientists, hardware engineers, software engineers, manufacturing teams, optical engineers, physicists, finance, sales, marketing, all working together in confluence to achieve our dream of scaling 3D printed products to mass production. My background is in polymer science and engineering. I obtained my PhD in polymer science and engineering at University of Massachusetts Amherst in the Boston area, all the way on the East Coast. And I did not directly work with 3D printing, but I was looking at mechanical properties of elastomers and gels, and that expertise is really helping me study durability and mechanical properties of Carbon's elastomeric materials. So again, very excited to be here, and I'm new to the world of 3D printing, so really looking forward to networking with you all.
Thank you. Let's start with a few understanding of what is happening in your lab. Ramona, I'm wondering if you can help answer these questions. We would like to understand some of the important challenges of additive manufacturing, industrial adoption that your lab is addressing, and specifically if you can share with us some of the materials that you're developing currently for AM processes.
Sure. So, just additive manufacturing and native to Industry 4 is, just slated to change the entire manufacturing enterprise by 2030, right? But despite the hype, additive has not yet prevailed in industries due to multiple major drawbacks, for example, especially in metals, right? So, for example, very high cost per part or limited material selection. Just one of the most commonly used metal additive techniques is powder bed fusion, for which, the machines can be just priced at well over $1 million, $2 million, and the materials can cost as much as $50 per pound. So in addition, we know there are potential hazards to work with loose reactive metal powders, right? So through this process. But recently making, just metallic component by using a desktop extrusion-based additive method we call fused filament fabrication or fused deposition modeling has absorbed the attention of researchers and industries as a cost-effective and material-efficient technique, right? Just by this technique, if you have for example, the metal infused polymer feedstock material, so you can make filament, put it in the nozzle, and layer by layer, so you can print whatever design you would like, right? So the FFF machine, I mean, are open source technology and accessible to almost everyone due to their low cost. So if you can purchase a desktop low cost FFF printer with $200 or less. Just the technology is more accessible, far safer, and more user friendly than just conventional metal additive techniques. But just the metal FFF is a young niche, and it's still in infancy. And the available knowledge for developing just functional, fully metal parts from a wide range of material selection is still very limited. So I mean, just the call for development of novel feedstock material based on metals for this technique tailored towards a specific application is exceedingly high in the next few decades. Just it's also important to note as additive matures, multi-material and hybrid advanced composite material will gain importance. And they leverage a diverse set of material property and functionality, right? For example, mechanical, electrical, thermal property all together. So, I mean, the future is more than metals, and there is a multi-decade trend underway, just to transition part from metals, just to advanced composite material, which are lighter, stronger, and offer greater efficiency. So within the integration of additive manufacturing, for example, with nanotechnology, so we can, have unit possibility for developing such advanced non-composite material compatible with a, for example, low-cost 3D printer, right? But again, still there is a significant gap in our understanding and technical knowledge on integrating a variety of material into low-cost 3D printed in a composite or non-composite layout. For next generation, for example, functional devices, right, such as energy storage, sensors, just catalysis, and so on. I mean, just metal FFF and composite FFF share many key process advantages, right, over conventional manufacturing techniques. And by having easy point of need manufacturing, the parts can be printed when they are needed and precisely where they are needed. And just with just a desktop simple 3D printer low cost, just parts can be printed on site with shorter lead time. But on the other hand, another main downside of additive is poor surface quality and surface topography imperfection that impact functional property, right? And they cannot be addressed by only optimization of 3D printing process parameters. So therefore, we do need some efficient surface post-treatment, right? To enhance the surface quality of external and especially internal hard-to-reach surfaces of complex 3D printed parts. So I mean, just as printed parts do need some surface qualification, just technique of post-processing before we can use them for end-use application. There are the main challenges and downside of additive manufacturing hindering its broad industrial adoption. But just in terms of the current material that currently we are working on in my lab, so we are working on development and optimization of novel advanced polymeric composite material based on multiple natural fillers, biopolymers, metal-infused polymer, recycled metal powders, right? Compatible with a low-cost desktop FFF 3D printing system for low-cost point-of-need manufacturing of metal and composite. I mean, we are here in my lab to address accurate additive supply chain challenges, shortage of available material for additive, just faster additive adoption by the manufacturing masses, accelerate development of in-house expertise, right? So we are here to help empower engineer and designer to design more game-changing parts for the end-use application for the future. Yeah.
Thank you. Thank you so much, Ramona. Nadia, I want to quickly go to you to help us understand where do we see material innovation in additive manufacturing occurring in the nearest future?
So Ramona touched on a number of important points as the challenges, and I think we can learn from those challenges and kind of expand. I can talk more on the metal side. Specifically, Ramona specified hybrid and composite materials. So we see a lot of hybrid manufacturing happening. In other words, hybrid manufacturing could encapsulate either a combination of subtractive and additive manufacturing in order to improve on your underlying materials finishing, which surface roughness is a big question mark on how can we improve on that finishing of our parts. Another way for hybrid manufacturing is by joining different AM techniques. So we've been, for example, looking at how to utilize bonding of dissimilar materials, dissimilar metals, by using powder bed fusion as well as deposition. So how can we utilize both the advantages on those technologies and by combining them together, as well as improving on the small feature size where we need to improve on that, and where we don't really have that limitation on our geometry, then perhaps we can use processes that are not as expensive or as complex to be adopted. Other than that, functionally graded materials are also of high interest at the moment, mainly because you can make your material behavior adapted for an application that you have in mind by functionally changing the composition of your material using a single material or using multiple materials at once. Alloy design is another area where materials innovation is going to be very important. So trying to understand the behavior of alloys that we haven't perhaps studied as much. One example to touch on the synchrotron use is understanding the formation of defects in 3D printed materials. In a synchrotron setting, you are looking in real time at the interaction between your heat source, for example, a laser beam, as well as your substrate material. So in aluminums, for example, the adoption of aluminums for 3D printing may be limited because of formation of hot cracking. And so that is an area where in situ monitoring and experiments that are performed at the synchrotron source can support in understanding where would be the formation and what is the process of that formation of defects. And we can translate that into the adoption of additive manufacturing by providing guidelines of what we have studied in situ.
Thank you, Nadia. Sarah, I'm wondering if you can follow up with some understanding of this, if there are ways to increase the speed or productivity of innovating material, finding new material to work with. Um, how has you been addressing this type of issue?
Yeah, and this is something I would love to learn from others on the panel or even other participants, in the chat. But I guess there are two good ways to accelerate materials discovery, right? One is computational. So this includes using machine learning, AI techniques. I mean, you can think of thousands of combinations of materials. You just take a look at the periodic table and select several elements and figure out using computational methods like density functional theory, which is called DFT, to figure out, or even something like CalFed or Thermal Calc, which are all software, computational software, to figure out how these combinations work and what kind of materials you will get, or even maybe some of their properties. So a lot of this simulation side to kind of tell you what are these materials even possible? Can these elements actually merge with each other? And I think that has totally changed the game with materials innovation. I'm more of an experimentalist, so I can definitely gear people toward the experts on these computational efforts. But experimentally, there are a few ways as well. One is especially with additive manufacturing or 3D printing, you can use high throughput testing methods. So I mostly work with directed energy deposition, metal additive manufacturing. For those of you who are not fully familiar, it's actually where you deposit powder into a metal melt pool instead of having a powder bed. And when you deposit these powders, you can actually have multiple powder streams so that each stream can be a different material. For example, let's say you want to make a material that is partially titanium alloy and partially stainless steel, or maybe your bottom layers are more steel, your top layers are titanium. So as you deposit these powders, you can tune in real time how much titanium you want in a layer, how much steel you want in a layer. But you can also use this method to just explore this whole material space. Like let's say you have 4 to 10 powder feeders, and each feeder can have like a different element or a different alloy, and then you can just build these little cubes or little clads of all the combinations all on the same plate. So I want to shout out to, there's a speaker in this conference, Melanie Lang. She runs Form Alloy, which has a really nice, I think like 16, maybe 32 powder feeder capability where you can mix and feed like all types of materials with these powder feeders. So that's a really good way because as soon you can print them really quickly, all these different combinations, and then actually check them, you know, test them out, look at them under the microscope, see if they actually match these computational predictions, right? I think the computational stuff is amazing, but sometimes you need to see if like the experiments match and what's the real life is going to be. So I've done a lot of this high throughput, like mixing and matching, using the powder feeder just to come up with these different recipes and then see, do they actually work? Do they actually fuse together? Because we know the process can be crazy. And then another method experimentally is a lot of times just helpful to have really good background on maybe just one material. You know, let's say you have extensive background on titanium alloys. You've done a lot of titanium alloy work, and materials innovation isn't necessarily coming up with new recipes, but it's just making titanium alloys better. So it could mean maybe dosing a titanium alloy with a little bit of like molybdenum or a different element just to make it more strong or have a higher melting point. Or you can use the exact same chemical composition for your titanium alloy that you've been using, but use some kind of other method to refine the grain structure, right? To like change the crystal structure and make it a stronger material or make it more resilient. So as an example for this, I liked how it was mentioned that hybrid processing or using a second process after the 3D printing process is helpful because you can use like a deformation process to kind of create a nanostructure for an alloy. An example is there's a professor at Oregon State, I think Dr. Pasabani, who's worked with tungsten alloys. Tungsten is just so difficult to melt, but she's been able to print these and then actually use like dynamic torsion to make a nanostructure. And so, I think there are ways, like if you're familiar, you can tune the type of material that you want to make.
Thank you so much, Sarah. There are already so many questions for you. People are so excited about this, but we have to go through others. Shruti, Carbon is using all of the different research to bring innovation to life so people can actually use this innovation. We would like to understand if you want to share with us some innovations that in polymer material science that Carbon has created over the years so that we can learn more.
Yeah, definitely. So, Addie, if you don't mind, I just want to share a few slides that I have. Let's see. Hold on. Okay. If I go to window, sorry. Okay. Do you see my screen?
It's not fully loaded yet.
Okay. How about now? Let me know whenever you can see it.
You may want to reshare because it looks like you got into a trouble.
Okay. Let me try again, or I can just stop. That's fine. Either way. Do you see it now, or?
Yes. We can see you now.
Okay, perfect. So yeah, I guess to your question, I just wanted to highlight first what Carbon's unique technology is about. So I really like this phase map, which essentially shows the different 3D printing technologies specifically for polymers that are available today. So on the left, you see more of the heat-based 3D printing technologies like SLS, FDM, and on the right, it's showing some of the UV curing 3D printing technologies such as PolyJet and SLA. So essentially, for the heat-based 3D printing technologies, we get good surface finish and high resolution. However, it has some of the limitations related to porosity. And also, we're limited by the lowest feature size that can be achieved because the nozzle diameter can only be that small, and the size of the bead that is generated, it cannot be beyond below a certain length scale. Whereas for UV technologies, although you can print a nice 3D printed part, but it can be limited by good mechanical properties. More often, these UV cured polymeric parts are brittle, and they also lack good surface resolution. So Carbon's technology works at the intersection of UV curing and thermal curing. So essentially, if I go to the next slide, this process shows how Carbon's 3D printing works. So we have a platform which is lowered into this cassette, which is essentially a reservoir of UV curable resin. And we have sophisticated digital optics at the bottom, which actually project UV light into a sequence of images. And our 3D printed part is cured. It is UV cured as the platform is raised from the reservoir of liquid polymer resin, and it cures into this green part, which at this stage still does not possess the mechanical properties that are demanded of engineering and functional grade materials, such as those come from injection molding. So one of the unique features of our technology is that we take out this green part, which has been 3D printed, and then it's baked in an oven. Then it's thermally cured, and finally we get this 3D printed part, which has unique mechanical properties. It's strong, it's tough, it's durable, it has good surface finish, and also isotropic mechanical properties. So a little bit more in the technical side of things. So I won't go into too many details, but again, one of the unique features of the technology are these dual cure programmable liquid polymer resins. And essentially, we have arranged the polymer chains and the end blocks in a way. These are specifically, in this example, I'm talking about polyurethane resins, which during 3D printing, as I mentioned, the UV curable chemistry is activated when we shine the UV light during 3D printing, and we get the formation of a UV cured polymer network, which has some of the thermally curable parts, which are still trapped within this UV curable network. And this is the green part, which I was showing during the 3D printing process. And once the part is removed from the 3D printer, we wash it and spin it, and then it is ready for the second step, which is the baking step, which activates our thermally curable chemistry, and then we form what is an intertwined polymer network of UV cured polymer network as well as a thermal cured polymer network, which gives the final 3D printed part really good mechanical properties. So this is what is unique about Carbon's technology, and it has led us to develop a wide variety of materials portfolio ranging from rigid polymeric materials, some of them very comparable to traditional thermoplastics like nylon, glass wool PVT, possessing high functional toughness, temperature resistance, flame retardants in certain cases, used in automotive parts and housings, and variety of other applications like I have shown below. I specifically, or most recently, have been working on the elastomeric side of things, more rubbery, stretchy materials. We have, again, a wide range of elastomer materials based on their energy dampening, energy return, impact absorption properties. And one of our most famously used elastomers is in the midsoles of Adidas's running and functional running performance shoes. And then some of the examples from the medical industry, I would probably like to talk about the nasal swabs that were developed when the pandemic hit us a couple of years ago, again, using carbon materials and also a unique software feature, which is called as a design engine that enables us to generate lattices of different designs. So using the same material, you can actually, the software computationally brings about changes in the geometries of the lattices that again can generate different mechanical properties based on the end user specifications and product requirements. Um, so I think, again, just highlighting some of the successes that we have with our partners, and what is very exciting is that how 3D printing, great examples of how 3D printing has been, has taken the road from functional prototyping all the way to mass production of bicycle saddles, helmets. So soon this weekend, we'll see some of our NFL players actually wearing helmets using Carbon's DLS technology. We have Osprey backpacks, again, the readers, running performance shoes, and gloves. So I hope this gives a flavor of some of the different materials that Carbon's materials team, and as well as all the other teams working together in Confluence, has brought about.
Thank you so much for sharing that. Ramona, I'm coming back to you. The promise of additive manufacturing is that it's going to offer everything green. It's going to help us with recyclability. You can reuse material. We're going to have less waste. And this is one of the areas that the world has to move towards. I know that this is an important area that your team is working on. I'd like you to expatiate a bit about recyclability and sustainability, and how is that critical in material development, and how are you approaching that?
Yeah, sure. So as you mentioned, just the current work environment scenario necessitate innovative and more eco-friendly solution, right, to global challenges that meet material demand. So, for example, just sequestering carbon that has been removed from the atmosphere in products is a key way of tackling climate change, right? Or, for example, if you develop carbon negative material, bioplastic, biopolymers, or just a green composite material from forest and agricultural waste, for example, we can remove emission instead of releasing them, right? Um, I mean, climate change is really a material problem in that there is too much carbon in the atmosphere, right? And the question is that, so how come we cannot turn this into our biggest resources? So as you mentioned, my lab is currently just developing innovative material and feedstock and filaments to create sustainable and recyclable products for low-cost point-of-need manufacturing of metal and composite. But how? For example, we use just the different biopolymers, which it has just less carbon footprint compared to fossil fuel based polymer, and reduce greenhouse gas emission. We use just recycled metal powders through eco-friendly processes, for example, mold process, and we use natural fillers, for example, wood, hemp, right, that are eco-friendly. So such material are indispensable for sustainable development in the context of circular economy and circular manufacturing, which strongly focus on reuse, repair, remanufacturing, and recycling. It's critical to develop such sustainable material, feedstock material for low cost and less energy consumption manufacturing system, for example, FDM, right? To enable to fabricate multifunctional and multifunctional just parts. So and such recyclability and sustainability study just contribute to the recent Canadian government sustainability goals in 2030 as well, for novel eco-friendly solution to just global concern, and generate a circular economy model for Canadian industry and even beyond. So, for example, to prevent depletion of rich natural resources, for example, metals, and take a step towards accurate supply chain challenges. So we use the environmentally friendly, just processes to extract recycled metal powders. For example, carbon in nickel or carbon in iron are a low cost and recyclable rate. So to develop novel feedstock and filament for the low cost FDM 3D printer. So also, just implementation of circular manufacturing concept in designing advanced nanocomposite or composite material, polymeric-based composite material, just extend material lifetime and reduce waste to fabricate, just high performance and multifunctional parts for next generation functional devices. So, I mean, we are not here, just to produce waste for the next generation and that's it. So we are here to help to address the accurate, just supply chain challenges, to find a key way to tackle climate change. And as you mentioned, just working towards using green and sustainable material and feedstock compatible with lower energy consumption equipment to manufacture parts definitely is something of, just high importance and interest.
Thank you so much, Ramona. I feel like oftentimes when people advertise additive, there's a whole lot of focus on the green component of it. So it's actually very good to see your team really putting effort in bringing this to life as something that could happen for additive for real. Sarah, we would like to ask if you can share more about some of the steps to design a new material and what are some of the specific constraints that you have to design for when creating these new materials?
Yeah, I'll go into some of the examples that I've worked on. I think differently, and I'm trying to still figure out like a really good streamlined framework, because I think there's also a question about this, but it does require, or at least the strongest way is a combination of computational and experiments. But yeah, some of the steps that I take is, first of all, what kind of properties do you need from the material? Especially with some of the applications that I've been working on recently, something like strength or the ability to, something that's corrosion resistant or the ability to withstand really harsh environments is key. So we'll look into, first of all, the type of element or alloys that already have some of those abilities. Something like a refractory alloy, like a molybdenum alloy or something like tungsten, right? But then what usually comes as like a curveball is sometimes they ask for a lightweight, refractory, harsh environment material. And, if you look at the periodic table, tungsten and molybdenum are actually very dense, right? They are very heavy and they also have a very high melting point. So there's also this challenge of, are we even able to melt it or fuse it together? How do we even print it into a complex geometry? And so you kind of have to be creative in terms of the process. So not only in what kind of material composition or recipe do you want, but like, how are you going to change the process? Can you even like manipulate the process to give this lightweight aspect to it? So I will also try to share a slide to show an example. So one example, let's see if I can share. Should I do? Okay, I'll do share. Yes, share screen. I will just share my entire screen. It's gonna look weird. Okay, so hopefully you can see this PowerPoint presentation. So like I said, in a lot of my work, I use real-time imaging, so process monitoring during the process. There's a lot going on here, but what's happening is we're actually using a laser moving from left to right to actually melt metallic particles. And these particles that are, you see, just I mentioned in the first question, like we're depositing different elements into a melt pool, a liquid pool of metal. And we're depositing molybdenum, niobium, vanadium, titanium. The reason why we want molybdenum, niobium is that's your refractory, high density, Z, really harsh environment type of elements. But vanadium and titanium, they are also high strength, but they provide a lot of that lightweight material. And if you can probably see in the bottom there, these like little white bubbles, those are pores. So those were like, we didn't know how to control this. This is just like, oh, let's try and see what it looks like during the process, if we can actually melt them. But we could actually see like, oh, we're creating these bubbles, these pores. Sometimes, actually most of the time you don't want those pores, but if you're a lightweighting material, maybe you do want air bubbles or air pockets that are far enough away from the surface so they don't cause issues when a part is in use. And then they can, because they're just air, they create this lightweightness to your material already. So, and then another example is, let's say you do want to create a lightweight but tungsten nuclear reactor wall. So actually these are all like nuclear applications, but same harsh conditions that you would see like in aerospace, or now that climate change is getting worse, like with climate change. So can we create a tungsten part that's 3D printed but has a lot of pores inside that we can design for that, so it's still lightweight. It's a high Z or high dense harsh material, but it's still lightweight, even though it's usually the heaviest type of material. And this is really interesting for like micro reactors that the government's really interested in for nuclear energy. So those are some examples. It's usually pretty tough, and usually you need like a good framework of how to implement. Sorry, I'm trying to find my way back and stop sharing. Okay, how to implement, the properties that you want at the end, and then how to design that with the process, because sometimes. And there's another good question in the Q&A about like the chicken and egg problem with process and the material that you want. Sometimes you have to figure out ways to manipulate the process to create these bubbles for lightweightness, and sometimes they're accidental, like I just showed you, but you can figure out ways to manipulate them. And so that's more of like the really metal side, and I'm sure on the polymer side, it's maybe similar, but also very different type of design process. But I take a look at the properties that are needed first, or even the application, and then kind of move backwards.
Thank you so much, Sarah. We want to move back to Shruti. We want to understand if there are what are some of the biggest challenges faced by the industry in translating the innovations that are created in the labs to large volume production. It would be great if you could share a bit about that.
Yeah, definitely. Thanks, Addie. I think again in my academic research, I have been in chemistry labs in academia, and even here in industry, we start at the lab scale. Small cups where we are making our new polymeric resins, mixing them manually or in very small equipments or mixers, and testing out our formulations in terms of properties, whether they would be able to whether we would be able to achieve the targeted chemical, mechanical properties which are ideal for printing. But when we have to scale them to mass production, we have to move from cups to drums to totes, and this entire workflow from the lab scale formulation to high volume production. There are definitely lots of challenges involved. Just as an example, that for the elastomeric materials that Carbon is developing for Adidas's midsole, we start with this resin at the lab scale, but eventually for mass production, we have our contract manufacturer partners, and they are developing these resins in their factories, and they are our raw material suppliers, and we want to make sure that they produce the materials which meets our chemical and mechanical property specifications, for example, in terms of viscosity or the content of certain functional groups and things like that. Because if those specifications are not adhered to, then it will affect the final performance of our 3D printed part. So making sure that those raw materials, when they're developed at the suppliers, they adhere and they meet our specifications is very critical, and making sure that those raw materials are produced in a consistent manner is very important. And then secondly, how are they mixed? So again, as I described, we are making resins in the lab, we are hand mixing them or using small static mixers or small equipments to formulate our resins. However, at the industry scale, at the manufacturer scale, we have large blending equipments, we have MMDs, and it is very important that how changing the equipment and the various functionalities or variables of how those equipments are operated, it can affect the properties of our materials. Similarly, we have printers at our partners, labs, and the many factories where these parts are being produced. It is also important that they are printing the materials in a consistent way. So again, reproducibility, consistency, making sure that the raw materials that are being supplied are meeting the specifications. These are all big challenges whenever we are scaling the materials from lab scale to mass production.
Thank you so much. It is very important that we understand that the work that is being done in university actually have very good industrial use. While we think about that, we also understand that there are challenges that happens during this processing. Um, we're wondering if Nadia, you can talk a bit about how material innovations being developed by researchers is being adopted for industrial applications from your own perspective as a researcher.
Right, and that's a big question. I mean, we're all working towards the same goal, which is adoption of additive manufacturing by industry, right? Because of all the promises of being able to print complex parts with less waste and with a faster turnout. In terms of industry applications, I saw a question coming in also about the connection between material innovation and applications in industry and which drives the other one. I would say it's a two-way road because, as Sarah mentioned, you work as a researcher on developing your own alloys or trying to change those recipes for the metals, but then you always have in mind what are the operating conditions that your material is going to be put under. And so we have a big gap to kind of understand our AM materials from when they are printed to how they will behave in the lab. But then we always keep in mind that we want to test those materials under operating conditions that are translatable either to some energy application or to an aerospace application or others. We see the adoption most of the times in printing complex components. So you've probably heard about the GE fuel nozzle and how it has been printed by kind of consolidating multiple parts into one. But then in terms of other applications that would use innovative materials, as we were talking about hybrid manufacturing, for example, some of the applications could fall under energy for concentrated solar power cells. If you think about heat exchangers that are being implemented in the field. I'm glad Form Alloy was brought by Sarah because the team has helped our USU groups working on a design for additive for a heat exchanger to be used in renewable energy. And it is true that a lot of the times we, as researchers, have ideas on how we would like to innovate on our materials, but the question always comes down to, can we apply those findings and how do we translate them into the industry? So I think a connection between researchers, academics, as well as people who work on machines, so engineers and technicians, would benefit that circle of closing the circle of innovation on materials and then all the way to application. In terms of large components, I'm glad that Shruti mentioned about how we have to understand our material properties as we are going from smaller scale to large scale. And that's something that we should also tend to do. The adoption, to sum up, is happening in different sectors for energy, in transformational nuclear materials, as well as solar applications. And I can see that material qualification is the biggest step that is pushing us towards the more we understand about our materials and we can qualify them, the better and the more streamed is the application in industrial settings.
Thank you so much. I have two other questions that we thought are good extras that I would like to ask. This is to Sarah, and I'm wondering if you can share some unexpected challenges that you have seen when working with a material that you thought, oh, this material will be great. Now you come across a challenge that makes it difficult for you to be able to execute that.
Yeah, going back to that previous video that I showed with molybdenum, it was kind of unexpected to have so many pores. But another thing that was unexpected is all the other elements like to mix in together and they melted nicely. With a metal melt pool, you actually have a lot of stirring in this melt pool due to this high thermal gradient, and there's like surface tension. There's a lot of like, I guess, physics involved in this melt pool. And so the other element, all the other elements, excluding molybdenum, melted nicely, mixed together. They follow this Marangoni flow of the melt pool. However, it was weird because something like molybdenum, it's very heavy. So kind of like, I mean, you can think of a liquid melt pool as like water and you're skipping rocks. And when you're like dumping powders, it's kind of like skipping rocks, and maybe it'll just fall in and then get stirred and mix. But molybdenum, even though it's the heaviest one, it just wanted to float. And so we could not really get it to mix and melt, and that's the one we really wanted to melt. So that was unexpected. And then, but I think talking to people who had a lot of experience with trying to mix the similar materials, it made a little bit more sense, because something like molybdenum or some other elements, they're just more prone to like oxidation or reactions with oxygen. And that was unexpected. So it's like you learn so much with what happens in the process. I also know that like sometimes we try to just use our infrared laser to melt or some materials, but that wavelength of laser does not work with a lot of materials. So if you want to do something with copper, let's say, or aluminum, it's better to use a different type of laser, because it will absorb that laser better. So it's like you just have to learn so much about what's happening in this process and like all these reactions. And I wasn't when I first started in additive manufacturing, I was like, well, let's just print, and I'm excited to see parts. But like, especially with metals, there's so many weird reactions that occur. Probably with polymers too. I was just learning from Shruti's slide. I was like, wow, okay, those change. So yeah, those are some unexpected things that we've seen.
Thank you. I want to take this back to the polymer people because Shruti, it's very good to print cool stuff, to have all of these things looking like we're going to move from regular method of manufacturing to additive. But there are questions on the mind of people as to meeting functional requirements. Can you tell us a bit about some of the steps you are taking to ensure that the materials and also the 3D printed parts meet functional requirements today?
Yeah, definitely. So, Addie, just again, describing my role a little bit more, I am in the materials characterization team within the materials team at Carbon. So I am, one of my day-to-day job responsibilities do include testing our 3D printed parts for their functional requirements. So for example, for the rigid polymeric materials, we're very interested in looking at their toughness. But again, toughness is a metric which, especially for polymers that are strain rate sensitive materials, gets very tricky, because we need to measure our materials under loading conditions which are very similar to their application. So if our rigid part is going to be handled by operators, and there are chances that it can be dropped on the floor very often, so we want to make sure that we characterize its drop impact resistance. Then for our helmet lattices, which are used in NFL players, helmets, if they collide with each other, we want to make sure that we characterize their impact performance again at the relevant loading conditions. So that is going to be very high speed impact, and we have an Instron cease drop impact tester, which helps us characterize the impact absorption capabilities of our lattices. Specifically, I am working on Adidas's midsoles for the durability performance. So as you can imagine, they're being used by runners in high performance running shoes, and based on the runner's gait, the material is going to be loaded under compressive loads. So we want to understand that how do the cyclic fatigue properties of these materials, do they change with time? Would the material fail after a certain number of cycles? And for that, we have another Instron machine, for example, that's called the ePulse, and that enables us to understand the cyclic fatigue properties of these elastomeric materials. So again, I touched mainly upon the mechanical properties that I have been looking at, but we have a wide gamut of characterization techniques within our labs at Carbon, characterizing the chemistry. And I think I saw one of the questions related to shrinkage and warpage, and molecular weight of all the polymeric chains, what material gets reacted versus unreacted, stability of our resins. We add colors to our resins, so what is the pigment stability? Definitely this aspect is very critical, that we have 3D printing, we have printed the part, but does it meet the functional requirements specified by our customers? So we work with automotive, for automotive applications, dental labs, Adidas for performance shoes and helmets and gloves. And so different applications have different product requirements, and that's what we're striving towards for all our formulations. And we make tweaks, like one of our panel speakers was describing, again, to continue to push our materials to meet those high demands.
Thank you all for your contribution. Thank you all for sharing with us today about your various work. There are a couple of questions in the question box that I want us to quickly run through. I think this first one is for Sarah. Expansion of the material portfolio is critical to accepting additive manufacturing across several industries. Are you looking at expanding materials per industry need?
Yes, you do need to do that. So I think that's where it is, playing with the chemistries. So it's tough. Usually when you want to work with industry, and Nadia mentioned this, like usually materials and parts need to be certified and qualified, right? There are these specific standards that are say, like, okay, this material composition is certified to be used for this application. And even when you buy these metal powders from off the shelf, usually they are already qualified or certified to have this recipe to be used for all these kind of applications. But I think, I mean, if you're mixing and matching and like developing some new recipes, you need to kind of push that envelope and be like, hey, like, have you thought about this very traditional, maybe stainless steel, but you dose it with these other elements, or maybe you instill maybe air bubbles or something, or put a coating, and this could be what you use. It's just sometimes it's hard to get through that qualification and certification stage, but you can just try things out. And I think that's so I feel like, as a researcher who works on very fundamental stuff, like I really want to understand, the industry needs. Right now I'm kind of like, I feel like I'm playing around, but yeah, I mean, it's important to kind of go through that rigorous process, like, hey, this is what we can actually use to put in space or in a nuclear reactor.
I love that we have people from the industry listening here today. I feel like it'd be great to have an ecosystem where industries can talk to universities and really find a synergy in terms of having an understanding of What do we need? What are people asking for? What is it that would launch a market in a particular area? And then convey that to the academic. So as you develop, you can help us focus in on different materials that can have very good industrial needs that can help us at least allow the general public to accept additive more. I have worked in the aerospace, automotive, medical space of additive, and there are some materials that we're still waiting for. They're important. If we don't break even, if we don't get those materials out, our acceptance will be low. So if you're on here, you're listening to us, you are in the industrial space, you're also craving some materials, please reach out to Sarah and hopefully we can form some sort of a consortium and start this conversation. I think it's a necessary one for our community. There's a second question here. Other than chemistry, do you focus on other material properties since different AM technologies are sensitive to different material properties? How do you prioritize your focus? I feel like this question still goes to Sarah.
Yeah, focus on, yes. So I mentioned that I mechanical properties like strength and toughness, and I think those are similar ones on the polymer side too. But trying to see that question again. I
already marked it as gone.
Oh, okay, yeah.
I think the person is thinking you talk to us a lot about chemistry as your priority. So there are other areas, for example, maybe PSD and on other areas. If you're prioritizing other material properties, maybe for even powder or the real product.
Yeah, so I think Ramona can talk about this too, because other than chemistry, you can look at just the powder shape and size. You can look at how a material even, so the shape and size is really important for if we want to recycle powder. And we were looking into recycling metal, like scrap metal, right? Usually the metal powder that we have, as I showed in the video, are like really nice and spherical. You have to atomize it. But what if you want to use scrap metal that's the same material, but it's just like a very different shape and size, and maybe it has like impurities, which goes back to chemistry. But it's also how does it react with your process? So if you try to flow little spherical balls, it can flow really nicely. Let's say you try to flow like scrap chips or metals, it's gonna all like clump together. It's gonna like be a really shaky type of process, or maybe you have to use some kind of vibrational method to actually shake those out. So you have to look at like all the, that's why I think coming up with a framework of like co-designing materials and the process and maybe the final geometry. If someone has like a magical co-design framework, or maybe, yeah, like Addie, you said, it has to be a huge consortium, group effort where we know if you have this type of material that has this chemistry, but also has a shape, size, reacts with a laser or reacts with a process this way, like this is what you're gonna get. And it's just, so I could speak to that like for hours, and I don't want to take all that time. But
I would say that you have to wait after, because it looks like there are so many people with questions for you. Shruti, someone is asking, how do you characterize?
Sorry to interrupt you. I can add more to the previous question. So because just when we are working with metals, so the story is different when we are working in polymer and polymer composite material. But just for a polymer composite material or nanocomposite, so we have a lot of properties that we need to investigate, just in details. For example, when we, for example, work with biopolymer, let's say PLA, and kind of metal powders, recycled metal powders, or for example, just carbon nanotube or other stuff, right? Or for example, wood natural filler. So we need to, just look at the flowability of the feedstock as well. So the viscosity studies are very important, for example, right? So for example, by using a capillary rheometer, so we can find out, okay, so how is this material, this new feedstock is viscous enough, just to compatible with our 3D printer. And I see a question here that how you meet the industry need. or do you meet the industry need? And as Sarah mentioned, yes. So it depends on application. Shruti mentioned as well. So for example, I would prefer to work with a low-cost desktop 3D printer instead of, for example, a kind of powder bed fusion technique that is $2 million, right? So with $200, I can purchase a desktop and make everything, just compatible with this 3D printer. But there are a variety of properties, just before making the filaments, for example, after 3D printing as well. So we have, as Sarah mentioned, for example, the we need to look at microstructure, the size and shape of particles, even metal or just nanoparticles are very important because it affects the final properties, it affects the flowability, or when we 3D printed part, so even just the mechanical property, for example, how strong is this material, or the fracture toughness, for example, if we use this for biomedical application, for example, we develop a composite material out of ceramic and polymer, right, for dental restoration. So we look at the fracture toughness, for example, right? So I mean, both in process, so pre-process, in process, and post-process properties are important, and it depends on application. It depends on what just 3D printing techniques are used, what material. So we are going to develop compatible with 3D printing.
Thank you. There are more questions in the question boxes, but we don't have a lot of time any longer. I would stop here, and I hope that the panelists stay around. And if you have questions for them, please find them in the different rooms and stop by. I'm encouraging again university partners. I'm encouraging industry partners to look for university partners. I actually intentionally brought a lot of university professors to the forefront because it is important that we realize how much work is going on there so that we can collaborate and take some of this innovation and bring them to our companies and really help us advance additive fast. Thank you, all of you, for your time, for sharing your expertise with us. Thank you, our audience, for being faithful. I hope you've been enjoying the technology track. Well, please come back in the afternoon. We have another fantastic lineup for you. Thank you, everybody, for your time. And we'll go on break now. Take care. Bye.
Thanks, Andy.